All right, solutions. Brass. Here we see a brass instrument. It is a solid solution of zinc and copper, and pretty much all alloys are. A solution is a homogeneous mixture of one or more solutes and a solvent. So if you have two different pure substances together homogeneously, you have a solution. Homogeneous means it's exactly the same literally everywhere. No matter where you take a sample, you should get the exact same results every single time. The solute is what gets dissolved. The solvent is what does the dissolving. And a solution does not always refer to just liquids. You can have solid solutions like we just saw with brass, or we can have gaseous solutions like air is a solution of nitrogen, oxygen, argon, and carbon dioxide. If the solute and the solvent are the same phase, they're both solids, they're both liquids, or they're both gases, the one you have more of is the solvent, the one you have less of is the solute. If you have two different phases, like sugar and water, when you're done mixing it up, look at what phase it is. And that's the phase of the solvent. So if I have solid sugar and liquid water, and I mix them together, I end up with a liquid. And therefore, water was the solvent. The solution will always have the same state of matter as the solvent, because the solvent is what does the dissolving, and the solute ends up within the pockets of the solvent. That's just trickier when they're both the same phase. It's just the one you have more of is the solvent, the one you have less of is the solute. And so with air, nitrogen is the solvent, because air is 78% nitrogen. All of the components of air are a gas, and the one you have most of is nitrogen. Soda is a mixture of sugar and water. Which substance is the solute? Which substance gets dissolved? Sugar, excellent. Because your final solution is a liquid like water. Water was the solvent. Sugar is the solute. A solution is prepared by adding 25 milliliters of ethyl alcohol to 75 milliliters of water. Which is the solvent? Well, they're both liquids. So the one you have most of is the solvent. So water is the solvent. And here we have different types of solutions. Gases dissolved in gases, like air. Gases dissolved in gases. Gases dissolved in liquid, like a soft drink. You buy a pop. It's bubbly. There's carbon dioxide gas dissolved in the water. And therefore, we have a solution. Liquids can be dissolved in liquids, like antifreeze in your car. It is ethylene glycol dissolved in water. Solids can be dissolved in liquids. This is the most common thing we think of as a solution. You dissolve salt into water, sugar into water, instant coffee into water, instant tea into water, Kool-Aid into water. There's lots of things that dissolve into water to make a solution. And so that's the most intuitive example. Gases can dissolve into solids. Platinum and palladium metals actually can absorb a lot of hydrogen gas, and so quite a bit of hydrogen gas will dissolve into those metals. And solids can be dissolved in solids. This is pretty much all alloys. We talked about brass earlier. Bronze was one of the very first alloys humanity created, and thus started the Bronze Age. Other notable examples, surgical stainless steel. And it's an exact recipe of different varying amounts of different metals to make that solution. So a true solution will be a homogeneous mixture. To be a true solution, the dissolved solute must be molecular or ionic in size, less than 1 nanometer in size. If the particles are greater than 1 nanometer, but less than 10 nanometers, you'll get a colloid. Like milk. It's permanently suspended, but it's not a true solution. You can't see through it. And if you ever want to test it out, dump a bunch of salt in your milk, and you'll see all the milk solids will just precipitate out then. And if the particles are bigger than 10 nanometers, you have a suspension. If you let it sit, things will sink to the bottom. So we have true solutions, colloids, and suspensions based on how big the particle size is. To have a true solution, the particles must be ionic or molecular in size, 1 nanometer or less. They can be colored, but they're transparent. Solutions are always see-through. If something is not see-through, it is not a true solution. So even if it's colored, like grape Kool-Aid, you should be able to see through it. If you shoot a laser at it, it should go through, even if it's colored. The solute will remain dissolved and does not settle out. And the solute can be separated from the solvent by physical means, usually evaporation. Solubility. This tells you how much of a solute can be dissolved in the solvent. And you have to give a specific amount of the solvent, and you must give the temperature. Because if you change the amount of solvent or you change the temperature, you change how much could, in theory, dissolve. So 27 grams of potassium bromide dissolve in 100 grams of water at 23 degrees Celsius. If you have two liquids, if they fully dissolve into each other, they're miscible. Like rubbing alcohol and water are miscible. They'll dissolve into each other infinitely. Ethyl alcohol and water are miscible. They'll dissolve into each other infinitely. Immiscible is when two liquids do not dissolve into one another. They form two layers, like water and oil. Water and oil are not miscible. If you have like a Caesar salad dressing, you can shake it up, and they'll temporarily merge. We call that an emulsion. When a water layer and oil layer are temporarily intermixed, but they'll separate out. They will not stay that way. Food chemistry uses a lot of that. Emulsifiers are chemicals that stabilize emulsions. And so you can have some water-based foods mixed with some fat-based foods and hold it all together with emulsifiers. And those are chemicals that let those two phases interact with each other.
What is it in pots and stuff that makes them explode if they get too cold or too hot?
Well, if you get too cold, it would start freezing. And water expands when it freezes. It gets about 10% bigger. So if you're in a can, the water starts it gets bigger and bigger, it blows out of its can. And so when they freeze, it's because the water's freezing into ice, and it starts expanding when it forms ice and it blows through its container. If it gets too hot, like a pop, the hotter it gets, the less soluble the carbon dioxide gas is. We're going to see that when a liquid gets hotter, it can dissolve more solute, solid solute. But when a liquid gets hotter, it dissolves less gas, and the gas escapes. So at some point, if it got hot enough, it would blow up because all the gas is escaping. Like if you put Coke onto a stovetop and start heating it, you'll see all the gas escape, and you'll be left with super flat pop. So that's probably what's happening. It's just the pressure gets to the point where it blows through the bottle. I mean, those bottles are built to withstand a lot of pressure, though. So it takes a lot of pressure.
I was just wondering because my boyfriend passed away in his car the other day, so I was just wondering why. So it's a sticky mess.
Yeah, that's what happened. It got too hot. When it gets hot, the gas escapes, and once the pressure gets to a certain point, it will blow up. But cars can actually get really hot. If you leave it in a car and the sun's baking on a car, that car can get to like 150 degrees. You can get really hot inside a car. Which is why they always have those advisories, like you can't leave a kid in a car in hot weather, because within a few minutes, the inside of that car can be like lethal and kill someone. It gets so hot. So that's what happened. The pop blew up. It got too hot. In the winter, it'll freeze, and then the ice busts, and then you have a slushy mess. But the same thing, it blows up in the end. Solubility rules. How do I know when something will dissolve in water or not? There's a lot of complicated rules. In this class, we keep it simple. Rule 1. If the cation is a group 1 metal, lithium, sodium, potassium, rubidium, cesium, or ammonium, the compound will dissolve in water. So ammonium compounds and all group 1 compounds dissolve in water always in this class. Rule 2. If the anion is a nitrate or an acetate, it will always dissolve in water in this class. Rule 3. If the anion is a chloride, bromide, or iodide, it will dissolve in water except Silver salts, mercury 1+ salts, and lead +2 salts will not dissolve in water. So silver chloride does not dissolve in water. And that's why you can't use tap water when we use silver salts, because the natural chlorides in tap water bind up to silver and it gets cloudy right away. So silver, mercury, and lead, chlorides, bromides, and iodides are not soluble. The rest of them are. Sulfates are soluble, except silver and calcium sulfate are slightly soluble, and barium, strontium, and lead sulfate, lead +2 sulfate, are not soluble. Slightly soluble means a little bit dissolves, but so little you cannot tell with the naked eye, so less than 1%. Chemically, that's a big difference though, because if a little bit dissolves, it's biologically active. Whereas if none of it dissolves, it is not biologically active. And that's why when they image intestines, they choose barium sulfate, because it's not soluble, it doesn't get into your body, but it produces a good image. And so you drink this milkshake of barium sulfate, and it goes all the way through you, letting them take good pictures of your intestines, but then it leaves your body. It never actually chemically gets inside of you. Whereas if something is slightly soluble, it will. A little bit of it dissolves in water, and that part is biologically active. So barium is extremely poisonous. So if you use a slightly soluble salt, that would probably poison someone. So it's really important. It's a small difference, but in biology, it's a big difference. Any questions on that?